a group of British rocket scientists are making the final checks before testing an experimental rocket engine.
Console armed.
Defying all conventional wisdom, one man has pursued a dream his entire working life. Lead engineer Alan Bond believes he is now on the threshold of realizing his dream, to build a revolutionary spacecraft that achieves Earth orbit in a single leap.
3, 2, 1, into sequence.
If their calculations are correct, their revolutionary design will herald a new era in spaceflight. This is the story of how a small and talented group of British engineers overcame personal adversity, shrugged off government intransigence, and defeated the Official Secrets Act to pursue a dream. A dream that began in a boy's back garden shed.
It's traditional in Britain that all things start in a shed. And we've kept up a long tradition on that.
Alan Bond's passion for space travel began at an early age.
The background really starts sort of back in the 1960s. Going back to my childhood days, I sort of looked at Dan Dare and saw that Dan Dare was not constrained to sort of messing about on planet Earth. He'd got a whole solar system at his disposal. Since those days, I've always felt that the human race has got much more ahead of it than just being confined to the surface of one little messy planet. As a teenager, I began to build my own rockets and really got to grips with what the problems were of getting into space. It very quickly became apparent that rockets were very limited in what they can actually do.
1, 0.
And from a very, very early stage, I realised that we weren't going to get Dan Dare out of the existing sort of rockets. We'd got to have something better.
This is a new sound. The sound of a space age. The sound of the Blue Streak rocket.
Nonetheless, the possibility existed for a long time throughout the 1960s that if we could just make the rocket engine a little bit better, a little bit more efficient, that we might be able to come up with an overall vehicle which did not have to throw chunks of it away to go into orbit. The idea was out there that we could and should do better. As it happened, we didn't get very far with that. And all around the world, there were a lot of people that realised that rockets in the form that we'd got them were just not going to deliver in the long term the kind of transport technology we were looking for. So virtually every aerospace company in the world was trying to do better. This is where a rather fortuitous sequence of events occurred.
Back in the very early 80s, we had a meeting that was organised by the French. The French wanted to come over and tell us their plans for Ariane 5. They had plans to put a winged mini shuttle on top of it called Hermes. Alan and I, who've known one another for a long time, sat at the back of this meeting and we said, this is dinosaur reinvented, the 1950s United States Air Force thing. There must be a better way of entering the 21st century than going with this antique technology.
In round about 1984, I had a meeting with Bob Parkinson and John Scott from Rolls-Royce in my office at Culham.
Well, the story was that Alan had been working on something quietly. Nobody was quite sure what it was.
I'd always been interested in pushing propulsion much harder. Whilst the solar system and trips to the moon represent a serious challenge, I'd been interested right from my earliest days in going much further than that, and that drew me into more advanced propulsion, nuclear propulsion. One of the things that came out of those studies is that if you have a hot nuclear reactor on a rocket and you have cold liquid hydrogen, I realised that you could replace the nuclear reactor with hot air at around about Mach 5, and that opened up the prospect of a whole new range of engines that no one had considered before.
But then one day he turned up at our house, literally at home, and he said, I want to talk to you about a possible new propulsion system that could actually sort of completely revolutionise rocketry as we know it.
Alan's visionary thinking had come at the right time. The world was growing tired of the ever-mounting cost of reaching space.
The world was beginning to suffer from the cost of launching satellites more and more, because more and more people wanted to put up small clusters, communication things, land resources, all the usual things, which at the moment, or still to this day, are being launched by totally expendable rockets. Nothing comes back except bits of wreckage.
To reach orbit, conventional rockets burn tons of hydrogen and oxygen every second. But when the fuel is spent, empty tanks and rockets are simply jettisoned to burn up in the planet's atmosphere.
Booster officer confirms staging a good solid rocket booster separation.
Shut down. CRDs have shut down. BDM fire. And set.
What took thousands of man-hours to make has a working life measured in seconds.
So people wanted cheaper launching things, and the only way to make it really cheap is to make it like an airliner.
So I tinkered together the blue book and passed it to John to find out what his interest was going to be on it.
It's pages and pages of theory and numbers. We turn to the back. Here we are, paragraph 7, conclusion. The report has outlined a proposal for an air-breathing engine which may allow a single stage-to-orbit space transportation system to be realised. Now, normally, if you talk to people about that sort of concept, they will tell you it can't be done.
I examined all the rocket propellants that were available, including some that you wouldn't like to work with. And you just cannot hack it with rockets. So you've got to make use of the atmosphere, same as any other aircraft does.
Alan turned to his old friend, Bob Parkinson, for help.
Alan rang me up to ask me a question about propellant chemistry, and the discussion over the phone, we said, it sounds like we've been working on parallel lines. We ought to have a meeting together.
Bob was thinking more about the actual vehicle side of things, and I was thinking more of the propulsion side of things. The great thing about Bob is that he'd moved to British Aerospace, and he also, because of his very innovative character, had the ear of the senior management, and as a consequence he was able to get the project into British Aerospace, and out of that came the HOTOR project.
The basic idea was simple enough. Conventional rockets burn a mixture of liquid oxygen and hydrogen. Hydrogen is an ideal fuel. It's light and generates huge amounts of thrust. In comparison, the oxygen it needs to burn is bulky and very heavy. But Alan Bond thought he saw a way to cut HOTOR's need to store that oxygen on board.
It was obvious the atmosphere has to play a part in getting us into space.
Bond's breakthrough was the idea that HOTOR could steal oxygen from the atmosphere.
And the whole idea of this was single stage to orbit. That was the key bottom line. Now, to do it, if you look at the amount of work you've got to do to get into orbit, it says use as much oxygen as you can from any source except what's on the vehicle. And so you drive yourself into the area of saying, well, how far can we go as an air-breathing machine? And therefore you can lean heavily on gas turbine technology, which is well established, and only use rocket technology when, putting it simply, you've run out of air.
Together, the three engineers secured funding from the UK government, British Aerospace, and Rolls-Royce. In those first heady days, Alan's dream looked as though it was becoming a reality. Bond's theory worked fine on paper, but experiments in the lab soon brought disappointment and delay.
There were several problems with Hotel. One was the actual design of the aeroplane itself, which was a magnificent attempt. The other was the engine. There were issues over the engine.
To reach orbit from sea level, Hotel's engines would have to work flawlessly at extreme temperatures.
The air comes in at 1,000 degrees centigrade as it slows down. And you can't put that through a compressor. In fact, it's very difficult to even design the airframe to stand it for very long. And so the key that Alan came up with is to take that air coming in, accept it in a heat-resisting duct for the first little bit, and then cool it drastically. And Alan's first choice was to cool this thing right down to just above the liquefaction point of the air which we breathe. Now that's a long way down, but it could be done.
Bond's second breakthrough was how he planned to cool the air entering Hotel's rocket engines.
Got hydrogen on board this vehicle, which is a wonderful coolant.
By using Hotel's liquid hydrogen fuel to cool and compress the incoming air, Hotel only had to carry small amounts of oxygen for when the vehicle reached space, saving weight that could be used to carry cargo.
Now what we've got here is a typical experimental heat exchanger from the Hotel program. The liquid nitrogen went into these tubes at the end, all the way through these fine tubes and out again the other side, and the air flowed through there. When we looked at the transit time for air going through the heat exchanger or pre-cooler, the answer comes out either between 1 and 2 milliseconds. And that's a pretty short time for all this heat to be removed bump. And the first experiments we did on rapid cooling showed us that within literally 4 to 5 seconds, the heat exchanger module would just frost up solid, no airflow through it at all. So it highlighted the key problem was not so much heat exchange, which we believed we could do, but how do we tackle the frosting problem?
Frost control wasn't the only problem the Hotel team encountered. Flaws in the airframe design soon became glaringly obvious. Richard Varville, a young aerospace engineer joining the team, grappled with the spacecraft's aerodynamics.
We'd basically made a mistake right at square one, which was to put the engines on the base of the fuselage. You have to go back to the origins of the Hotel project to really understand how this problem came about. We came from a background of vertical takeoff rockets, where, as you know, the engines are always on the base of the rocket and it ascends vertically and you've got all the tankage above it. On Hotel, that seemed like a good starting point, and so we ended up with this long, slender hydrogen tank sticking out ahead of the wings because it gave a very sort of structurally efficient configuration for the airframe. However, what we found was this very severe CG-CP mismatch.
When fully fueled, the weight of the hydrogen balanced the weight of the engines at the rear of the craft. But as the fuel was used up in flight, the center of gravity of the craft shifted backwards towards the engines. The center of pressure, however, was forced forward, leading to flight instability, or as aerospace engineers call it, a CG-CP mismatch.
To resolve this, we ended up making a lot of undesirable changes to the aeroplane, and in the process we lost, we reckon, about 4 tons of potential payload.
T-minus 10, 9, 8, 7, 6, 5, 4. We've gone for main engine start. We have main engine start.
From the outset, Britain had designed Hotel as a replacement for NASA's space shuttle.
America's first space shuttle, and the shuttle has cleared the tower.
Columbia had successfully launched a year earlier, with the specific goal of carrying payloads into space.
We have main engine start. 2, 1. Booster ignition and the final liftoff of Discovery.
Whereas a space shuttle could carry 22 tons of cargo, Hotel's design capacity of 8 tons had now been reduced by half. Unlike Hotel, NASA's shuttle was a two-stage-to-orbit vehicle, with the vast majority of the rocket simply discarded within minutes of takeoff. NASA described its space transportation system as a kind of reusable space truck, with each vehicle designed for a lifespan of 100 launches.
3, 2, 1.
In reality, in the 30 years the program ran, only a total of 135 flights were ever made. But the shuttle remains the only winged, manned and reusable spacecraft to have successfully reached orbit and landed again.
Main gear touchdown. Nose gear touchdown.
The shuttle program may not have lived up to its original billing, but it had the overriding merit that it actually worked. With all its technical difficulties and its payload capacity halved, the economic case for Hotel was now on shaky ground.
We do need to have a look at greater commercial involvement and just consider really exactly what the strategy is before we go into this highly expensive, I think not altogether well-directed space effort.
Despite Alan Bond's best efforts to persuade ministers of the technical and commercial viability of his project, they remained unconvinced.
The man in the street expects ministers to evaluate these hugely expensive claims, and until and unless these enthusiasts at home and abroad satisfy us there's good value for money, I think it's the duty of ministers to say we admire your enthusiasm, but that bill is simply too much.
With all government funding for Hotel now gone, Alan's dream was in tatters. As a last resort, he sought backing from Europe. He intended to take his engine design to the European Space Agency and continue his work there. But once again, the government stood in his way.
Following meetings between Bob and myself and some of the other people involved, it was agreed that I would apply for a patent on the RB545 engine. That immediately brought a classification. That was a disaster to the Hotel project. It meant that we couldn't talk to the European Space Agency, and we were never able to disclose at the time to the European Space Agency how this engine worked and what the advances in it were.
When the thing was classified secret, it immediately brings it to military use only.
That meant that I couldn't talk to anyone about it, and even got leaned on not to talk to anyone in the UK about it, including people at Rolls-Royce and British Aerospace. Of course, I had to fight that, otherwise there would have been no project. I was successful, but for the period up till 1993, many years after the project had actually finished, the engine remained classified.
In pursuit of his boyhood dream, Alan had started his career working on Britain's first attempt to put a payload into space. On the 28th of October 1971, Black Arrow successfully placed into orbit Prospero, an experimental satellite designed to test the effects of space on communications satellites. Ironically, the Black Arrow program had already been cancelled 3 months earlier by the government on economic grounds. To this day, Prospero remains the only British satellite to have been launched by a British-built rocket. For Alan, this was the start of a long and difficult relationship with government funding for UK space projects.
That is a problem in Britain. Britain these days is not visionary. There is a world out there. The Earth is a very, very tiny place in our universe, and I think you need a certain amount of scientific knowledge to appreciate that. And I think by and large in Britain, scientific knowledge is now a rather limited commodity.
Britain had closed the door on an active role in space vehicles, and with it, independent access to space. In America, however, NASA was still pursuing the concept of a single stage-to-orbit vehicle. In 1986, as HOTL was still underway, President Reagan had announced the United States National Aerospace Program. But rather than looking at exotic and unproven engine designs like Alan Bond, NASA wanted to build on the relative success of its shuttle program. It was firmly convinced that rockets were still capable of propelling a spacecraft to orbit in a single stage. Even as the United Kingdom was cancelling HOTL in 1989, in America, the government commissioned a series of technology demonstrators for a single stage-to-orbit vehicle. Whilst in the UK, Alan struggled to find backers for a successor to the HOTL project. In the US, Lockheed Martin was building the X-33 prototype. The X-33 was never completed before it too was cancelled. But in stark contrast to the position of the British government, the United States continued to pursue its goal of a reusable, single stage-to-orbit vehicle. Back in the UK, in frustration at the government's unwillingness to fund or even permit a successor to the HOTL project, Alan and two of his colleagues, Richard Varville and John Scott, decided to go it alone. They formed a new company, Reaction Engines, to continue development. The fledgling company was based in Cullen near Oxford, on the same site as the Joint European Torus, where Alan had worked before transferring to the HOTL project. The Joint European Torus is a research reactor designed to harness the power of nuclear fusion, the same energy that powers the sun. In such an environment, they rely heavily on computer modeling techniques to predict the behavior of their experiments before trying them out for real.
You could do an awful lot of modelling. You'd think that the aerospace business was the place that you'd learn that, but back in the 1970s, computers weren't very available. It took a long time to get onto a mainframe. Also, the actual analytical techniques that are used in the aerospace business at that time were very limited. So you tended to make things and break them, and make them and break them until they worked. Whereas the Atomic Energy Authority were building things that, if you broke them, were actually quite dangerous. So they had come up with a great deal more modelling than the aerospace industry had. I was fortunate that when I came to Culham to work on fusion, I learned a lot about that, and I was able to apply that. So given suddenly a PC of my own, I found that I was already on my old Spectrum able to do an awful lot that was still being carried out, say, in British aerospace.
Using the techniques he had learned at JET, Alan was able to continue working on HOTL's legacy without so much as a penny of government funding.
When we finished with the HOTL project, there were a number of outstanding issues. The computer modelling sort of using ideal conditions showed that there was tremendous actual potential behind the concept. But what we actually found when we come to wrapping all the metallic materials around it and the ceramics and so on is a lot of that disappeared for all kinds of reasons. And for the first sort of 3 or 4 years, the activity was simply to try and find out why we had done so badly with real engineering relative to the ideal. And that was down to the actual configuration of the aeroplane. We resolved that very quickly.
Computer modeling allowed the team to question every assumption behind Hotel's configuration and redesign it from the ground up.
We decided to literally start with a clean sheet of paper. And the way we did that was we took the engines off the base of the aeroplane and we put them actually onto the wing tips. With one bound, Jack was free, and we got a very efficient solution to that problem.
The solution was a complete overhaul of the airframe. The new craft was named Skylon. Although they had designed it, Bond's new company, Reaction Engines, would not build the plane, but develop the engines that would allow Skylon to fly. Whilst Bond continued to work on developing the original Hotel concept, NASA changed tack. It abandoned rocket technology altogether. Instead, it turned to a development of jet engine technology called scramjet. Scramjets work much like a modern airliner, but use their own speed to compress air into their jet engines.
Scramjets are air breathers that obtain oxygen from the air in which it's flying, and this characteristic allows for much more airplane-like operations with increased safety, affordability, and flexibility.
Scramjets are beautifully simple. They have no moving parts. A conventional jet has a series of blades to compress air into the engine. In a scramjet, however, there are no blades. The incoming air is compressed by the craft's sheer speed alone. But as engineers found, igniting fuel at Mach 5 is about as hard as striking a match in a hurricane, and keeping it lit harder still. Nevertheless, NASA was confident that scramjet technology would shape the future of manned spaceflight.
The ultimate goal of hypersonics really is twofold. One is to reduce the cost for access to space. The second goal, and probably one that's farther out, granted, but maybe 100 years out, but hypersonic commercial travel, I think, can be a reality someday in going anywhere in the globe in just a few hours.
Actuator bit on my mark. 3, 2, 1, mark. I show good bit.
In 2004, NASA's X-43 technology demonstrator set a new airspeed record for powered flight, reaching an incredible Mach 9.8. But scramjets can only function at velocities greater than Mach 4, and must rely on chemical rockets to boost them up to their operating speed. As a result, NASA now doubts that a single stage-to-orbit spacecraft will ever be achievable.
Console on.
Just as NASA was announcing the death knell for single stage-to-orbit vehicles, back in the UK, Bond's team had made a breakthrough in their engine design.
In 2004, we found an entirely new avenue which we could evolve with these engines, and the thermodynamics continues to evolve even now. So we're currently working on an engine which has half the fuel consumption of the Sabre engines that we designed in 1993 for the Skylon vehicle, which in itself was more than 50% improvement over the engines in Hotel. So I don't think we're near the end of what these engines are actually capable of at this point in time.
To bring the original Hotel concept to this stage had taken Alan's team some 15 years. Along the way, they'd had to overcome a series of obstacles which might easily have broken a lesser man. When Alan first formed Reaction Engines to develop Hotel's legacy, The engine he had designed had been classified top secret and its key features patented.
The actual patent restriction ended in 1993. The patent had actually been acquired by Rolls-Royce for a finite period of time, and it was quite clear that no further development was going to take place on that engine. So I set out to find a way to circumvent the patent in order that we could actually complete the work on it. Now, I wrote the original patent, so I'd written it in a way that I didn't think it could be circumvented. But what we had found during the course of the work were a lot of thermodynamic nuances within the engine, and that meant the engines were capable of things that in the 1980s I hadn't actually realised. Okay, we'll improvise it slightly.
Having overcome the legal obstacles, the team now faced a series of daunting technical challenges.
We need the thrust-to-weight ratio of a rocket engine, but we need the fuel consumption of a jet engine. So what we're doing is we're basically trying to stitch these two sort of technologies together. But in order to do that, we need to develop these lightweight heat exchangers.
The key to Skylon's revolutionary engine is its ability, like a jet engine, to compress incoming air. Then, like a rocket engine, to use that air to burn the onboard liquid hydrogen to create thrust. To do that, the compressed air must first be cooled until it nearly liquefies. And that's the bit that no one has ever successfully done before.
The Sabre engine is effectively a jet engine and a rocket engine stitched together. In order to make this work, we need these very high-performance heat exchangers.
It is the heat exchangers that make a single-stage-to-orbit vehicle possible.
Nobody's ever made this type of product before. No one's been able to make this type of product before.
The heat exchanger works a bit like a conventional fridge. Liquid helium is passed through a series of very fine tubes. Air passing over the tubes is then instantly cooled. The problem Alan and his team faced was to manufacture a heat exchanger with as many tubes as possible.
You can't just bend these tubes into any old shape. They're very unique items. They're unique to reaction engines. We've developed the manufacturing processes in order to build them. If you take one of these tubes in your hands, you can very easily just break it in two. So actually forming them into the shapes we need is a very difficult challenge.
The air is a very poor conductor of heat, so we have to do everything we can to strive for maximum compactness to maximise the heat transfer performance on the air side of the heat exchanger. So large quantity of these tubular flow channels of very small diameter improves the heat transfer performance. Now we've reached a practical limit on the compactness that we can achieve. That's where reaction engines is pushing the boundaries on compact, lightweight heat exchangers.
The challenge here is to cool the air whilst avoiding the frosting problem that had bedeviled the original HOTL project. It took the team years of research to develop a solution. But after their disastrous experience with Alan's HOTL patent, the team has chosen to keep their latest technology as a trade secret.
We've had a long research program developing the technology to stop this pre-cooler clogging up with frost, and that is unique technology to reaction engines. Trade secrets are how most industries survive. We have a number of key technologies, and rather than patent those, which basically declares it to the world how you've done it, what we do is we basically keep those secrets as trade secrets within reaction engines, and only reaction engines employees are familiar with that knowledge.
The last major technical challenge facing Bond and his team was getting as much thrust as possible from Skylon's engines, all the way from the runway right up to Earth orbit. Teaming up with Bristol University and Airborne Engineering, they're exploring techniques called altitude compensation to make their rocket nozzles ultra-efficient.
Once upon a time you could have a small nozzle for sea level, throw that away at the end of the first stage, and then have a bigger nozzle in the second stage which suits higher altitude, throw that away, and in the third stage have the biggest one you can fit. So the advantages that are gained by this altitude compensation are much more for a single stage where you can't throw anything away.
All rocket engines work by pushing hot gases through a nozzle to create the thrust needed to keep the rocket going. But as the rocket gets higher and higher, the size of the nozzle needs to get wider and wider to maintain maximum efficiency. Unlike the space shuttle, a single stage-to-orbit vehicle doesn't have the luxury of throwing away nozzles with each booster stage, so that the right size nozzle is always used at any given altitude.
The University of Bristol, to try and get around this problem, focuses on something called an expansion deflection nozzle. The idea is fairly simple. It's a fairly standard shape for most of for the outer contour, but there's a plug up the middle, a pintle, which goes up the centre of the engine and just causes a central void in the flow. As you get higher, it allows the flow to expand in towards the centre line, and so you end up with a more efficient engine.
Just a fire. They all ready? Yes.
What we learnt from these tests has been quite interesting. The rocket engine expansion ratio is bigger than the space shuttle, so the difference between the exit flow and the central flow is greater than the space shuttle. We ran that attached at 12 bar. The space shuttle needs to run at 200 bar to keep it attached. So we managed to achieve some fairly impressive results.
4.5 pounds of hardware and now control. Atlantis begins its penultimate journey to show up the International Space Station.
Having reached space, Skylon then faces the equally daunting task of returning again. The shuttle famously depended on thousands of ceramic tiles to protect it from the intense heat caused by re-entry. The Rocketeers needed a lighter weight solution. They took their inspiration from an unlikely source, an American spy plane.
It's drawn from the SR-71 Blackbird, which had a corrugated titanium skin. And when we started to look into the Skylon structure, we decided that the solution that other companies had tended to advocate, which is using honeycomb panels of sort of heat-resisting ceramic material, was actually not the right way to do it. And we could find a lighter solution by adopting the solution that the Blackbird had used, whereby we just take a single skin of material and corrugate it for stiffness, but also for sort of thermal compliance from the substructure from which it's mounted. During re-entry, the aeroshell is about 800 degrees hotter than the internal structure of the vehicle, so you've got a major thermal expansion mismatch there to solve. If you imagine this is part of the aircraft's skin, it could be part of the fuselage or the wing. Because of the corrugations, it has a certain amount of stiffness in this direction. However, it has relatively little stiffness in this direction. So this panel during re-entry could be perhaps 800 degrees hotter than the substructure from which it's mounted. It's silicon carbide fibres within a glass matrix, and this material is good to around 1,000 degrees C, we think.
May I have your attention, please? An 8-foot high temperature tunnel run is about to commence.
While Alan's team was drawing on American technology for heat shields, the United States Air Force had continued to develop the scramjet.
What we are going to do is we're going to take the X-51 Wave Rider. We're going to launch that from a B-52 at 50,000 feet over the Pacific Ocean, and then the vehicle is going to drop away. It's going to be accelerated by a solid rocket booster up to about Mach 4.5. The solid rocket booster will drop away, and the vehicle and the engine which is being tested is going to ignite and then further accelerate that vehicle up to Mach 6.
The Wave Rider is the successor to NASA's X-43 scramjet. but it is designed for conducting warfare, not space travel.
Everything we do at Edwards is flight test, and a lot of what we do is weapon systems and the short to middle term, helping the warfighter more directly. This is more of a long-term thing. The things that we're working on in the scramjet engine are going to benefit the warfighter 15, 20 years from now when we're able to utilize this technology to bring new capabilities to the fight. It's exciting though.
NASA had hoped that scramjets would deliver cheap access to space, but the US Air Force sees scramjets as forming the spearhead of prompt global strike, a military doctrine adopted by the US as part of the war on terror. Space travel is no longer a goal. As a means of getting a warhead to any target on the face of the planet in under 60 minutes, scramjets' disadvantages are of little relevance to the US Air Force. With scramjet technology firmly focused on military use, the Skylon team are confident that their own engine design will now emerge as the sole contender in the race to produce a single-stage-to-orbit spacecraft.
Our other main competitor in propulsion terms is the so-called scramjet, supersonic combustion ramjet. On paper, the scramjet has a sort of siren-like attraction about it because it's capable, in theory, of producing useful thrust up to some very high Mach numbers, perhaps Mach 10 or even 15 on paper. However, unfortunately, scramjets are completely unsuitable for propelling an aeroplane into space. A scramjet, like a ramjet, has no compressor, so it's not capable of operating from rest. It has to be accelerated up to some suitable Mach number before the engine can even generate any thrust whatsoever.
With all the enabling technologies that would turn Skylon into a viable spacecraft now established, the three Rocketeers' lonely years in the wilderness are at last coming to an end. The journey has been long and arduous.
My overriding feeling is just the sheer waste of time and effort that's gone into this. I'm now in my mid-60s. I really wish I was in my mid-40s trying to do the same things. My colleagues have spent a large part of their career in the wilderness. We could have done so much more. You have to remember that originally HOTL would have been going to orbit in the mid-1990s, and here we are at least 10 years on from that. It's so sad that it's taken us so long and there's been so much wasted time, especially so much wasted British industry in the process.
From his early work on HOTL to the present day, it has taken Bond and his team over 30 years to turn his vision of cheap access to space into something a lot closer to reality.
There have been many dark days, and the real dark days is when you carry a vision into sort of various government departments and you feel that people can't see past the first paragraph of that vision. But today vision seems to focus on bank accounts and material wealth and various celebrity programs and so on. The actual vision of doing something bigger on the basis that the future depends on it seems to have been generally lost.
At an age when many people would be looking forward to retirement, Alan continues to pursue his dream with passion and determination.
A lot of people have regarded me as having the vision. I've been fortunate that I've had a large number of colleagues around me who've also been able to share that vision. The potential that this technology can add to the science of propulsion is phenomenal.
Inspired from his boyhood days by the Dan Dare stories, Alan Bond has devoted his entire life to the dream of getting mankind into space. Shrugging off government obduracy, lack of funding, and international skepticism, he and his colleagues have struggled on against all odds. Now, more than 2 decades after the Hotel project was shut down, today's test will decide whether the pre-cooler actually works. And with it, the possibility of building an engine that would allow Skylon to fly. The very future of reaction engines itself depends on the outcome of this test. The years of hard work pay off. The pre-cooler works flawlessly. Alan's vision is finally taking shape. As of now, Skylon itself remains just a vision. So far, no one has come forward to actually build the first prototype. But such details are of little concern to Alan Bond.
We have absolute confidence in the technology. I've devoted well over 20 years now into developing this for the sole reason I'm absolutely sure that it's all going to work.
After a lifetime's devotion to this single dream, Alan can at last look forward to that dream becoming a reality.
10 years from now, the first Skylon-like vehicles will be flying into orbit. Someone will be looking at the Mark II. I like to think of Skylon as the DC-3 of the space business. And somewhere downstream there are the 747s and the 777s.
For the 3 Rocketeers, it has been a lonely journey. But as Alan approaches his 8th decade stuck on this planet, at last other people can now see his vision.
There is a new generation of people that do feel that there's some merit in what we're talking about. There's a generation of people within government departments in the UK that feel that there's some merit, and they have conveyed their views on that to the European Space Agency. And I do feel that we now are experiencing a sea change in terms of getting the project moving. We're standing today, I think, on the verge of a new era of transportation which will be brought about by these engines, and I think the possibilities are probably endless. In a few decades from now, we'll be able to put anything that we want in space as easily as we could get on an aeroplane to go anywhere else in the world. Although I'm slightly visionary, even I cannot see what the ultimate consequences of all of that are.